Okay, our last section comes from section 6-7, solving equations and modeling. We want to be able to continue work with our logarithmic and exponential equations. Today we're going to do it algebraically and with our graph, and also continue to explore the different real-life situations where logarithm equations are used. And we're going to start with that. But I'm noticing, to begin with here, that we have part of our equation incorrect. We're missing our fraction bars. So let's just add a couple fraction bars here. There's one there, and the other one is here. Okay. That'll probably make more sense now for our equation. So, on the Richter scale, and we know that's for earthquake magnitude, the magnitude m of an earthquake depends on the amount of energy E released by the earthquake as follows. M equals 2/3 times the log of the number E divided by 10 to the 11.8 power. Now, suppose that the magnitude of the earthquake measures 7.5 on the Richter scale. They want us to find the amount of energy released by this earthquake. So, we know 7.5 is our magnitude, and 2/3 times the log of E divided by 10 to the power of 11.8. Okay, looking at this, we should be able to undo this equation in a couple steps. Like right now, the 2/3 is out front, but it's a multiplier. We could multiply both sides by 3/2 to get rid of it. We could also turn it into the exponent. Okay, but I think in this case, multiplying by the 3/2 makes sense. So let's go ahead and do that for most of you instead of making the log side more complicated. So we can get rid of that times by 2/3 with a times by 3/2 on both sides. We will get just the log now of our statement E divided by 10 to the 11.8 power. On the other side, you could change that to a decimal and deal with our 1.5 times the 7.5, and we now have 11.25 if you want to work with decimals. Otherwise, change everything to fractions. Okay, so right now we're looking at, that's log form. If we rewrite log form, we could get exponential. So we know this is log in base 10 because we don't have anything down here as our base or subscript. So if we wrote this exponentially, we'd be saying 10 to the power of 11.25 has to equal E divided by 10 to the power of 11.8. And so to finish this problem, we would have to take our division. Now, a couple things, actually. So let's come up over here. We would have to finish by taking, and this is a divide by 10 to the power of 11.8. We would want to multiply both sides by 10 to the power of 11.8. So if we did that as our work step, they would cancel. Here we're looking at like bases, so add the exponents. And when you finish adding the exponents, that should be our E value, and we could do the math. So we've got the 11.8 added to the 11.25, and that should give us 23.05 for our exponent, which is not a real nice number answer, but go ahead and finish that, and we're looking at E. So that all equals E. So find the amount of energy released by this earthquake, 10 to the 23.05 power. And if you would calculate that, it's going to be a huge number. So finish, find out what that is, and it should be close to 1.12 times 10 to the 23rd. So just manipulating an equation that has logarithmic form in. Next example. So let's do two things here. Let's take and solve the logarithmic equation, the log of x plus the log of the quantity x plus 3 equals 1. Let's solve it for x by graphing and by algebra. So let's do the graphing first, because some of us probably wouldn't think about that. And what you have to do on this one is think of separating it. So you have basically two equations. The part that represents the log side, and then the part that represents the other side. And both let them be equal to y. So you'd have two equations, and here they are. Let y equals log of x plus the log of the quantity x plus 3, and y equals 1. We know y equals 1 is a horizontal line, so go ahead and finish the other. And you would graph it by typing it in or by hand. Okay, so I got our purple and our green. The green is the log equation, the purple is the horizontal line. And the question is, where do they intersect? Okay, because we're looking for what they share. And it looks to be this point right here is what they share. So most people would say, okay, 2, 1. But the question was, solve the quadratic. We only had an x in it. So we knew y was 1. So x is now 2, and our solution should be x equals 2. That's graphically. So again, separate into two equations. One for the left side, one for the right side, both set equal to y, and then look for the intersection. Secondly, algebraically, we have our equation. Let's see if we can get through the steps. Based on our properties, an addition with two logs in the same base should turn into a multiplication with one log. So we'd multiply those two. Now this is log form. It makes sense to either multiply or write it as a power of 10. So I didn't multiply it out. I said let's write it exponentially. So 10 was our base, to the first power has to equal that number. That number can be multiplied out, and we're looking at a quadratic then. That quadratic can be factored quite simply with the chart method. What multiplies to give me a negative 10, that adds to give me a 3. We get two solutions by doing the zeros, but as usual, we've been talking about, since the domain of a logarithmic function excludes negative numbers, the only solution we can take from that is the 2. The 5 gets thrown out as a bad choice, not true statement at this point. The only other thing we want to double check is, and we can use our book for this in class, review please the Newton's law of cooling. It's a formula, again, with quite a few variables and exponents and things in it on page 405 in our textbook. And if you have any issues or what the variables represent, how you might use it, that would be something we can share together in class. So, real life situations, being able to take logarithmic equations and graph and solve them algebraically was what we discussed here. So bring any questions and concerns you may have to class.